Hello. A few of you emailed me to ask about problem number 7 on motion worksheet 2. It was a little bit hard to explain through email because of referring to the various equations and writing out the words for delta x and things like that. So I thought I would solve that one in a video in case other people were having trouble with it. This problem says a rifle is fired and the bullet is accelerated in the barrel, which is 0.75 meters long. The bullet leaves the barrel with a velocity of 600 meters per second, and we're being asked to calculate the average acceleration of the bullet while it is in the barrel. Average acceleration is an odd phrase. Typically, it would be referred to as just acceleration, calculate the acceleration, or calculate the uniform acceleration, or calculate the constant acceleration. Average acceleration seems to imply that the acceleration is changing, and we are finding the average of a bunch of different values. That's actually not the case here. The acceleration is probably uniform. When a bullet is fired in a gun, the back of the bullet has explosive powder in it, and so when you pull the trigger, a hammer bangs into the back of the bullet, igniting this explosive powder, and there's this tiny little explosion that produces all of this gas. The gas has nowhere to go, and so its only escape from the gun is to push the bullet out, then the gas can escape behind it. So there's this bullet sitting in the gun, and then this gas is created from a chemical reaction, and the gas puts a lot of pressure on the bullet and accelerates it until it gets to this opening. But then, once the bullet leaves the gun and the gas escapes from the gun as well, the bullet won't continue to accelerate. The bullet will then continue on at whatever speed it had when it left the gun. So the barrel of this gun is 0.75 meters long. So that's the distance over which the bullet is going to accelerate. So that's equal to 0.75 meters. The displacement or distance or delta x, however you want to refer to that. This is a linear motion problem, so distance and displacement are essentially the same thing. We assume the forward direction is the positive direction. When the bullet is sitting in the gun, it's not moving, and so its original velocity or initial velocity is 0. The bullet is at rest until the acceleration begins. When the bullet leaves the barrel of the gun, it says that the velocity is 600 meters per second. Now, this phrasing, leaves the barrel, that means that that's the velocity here. That's the velocity at the end of the acceleration. So that's the final velocity. That's not the average velocity. And notice that there's a decimal point after the 600, giving that number 3 significant figures. And we're being asked to calculate the average acceleration of the bullet. You can see that the answer is this huge thing, 240,000. We expect to get this really big answer because this change in velocity is happening so quickly. So as you know, acceleration is equal to the final velocity minus the initial velocity over the time. Well, we don't have the time value. We have the displacement value instead, but You can imagine that the bullet is only in the barrel of the gun for a very short amount of time. And so if this time is a very tiny number, then the acceleration will be very, very large. So that's what's happening in this problem. Perhaps you can look at that list of equations and choose the one that you need. You have an equation with VI and VF and delta X and A that is here. VI and VF and delta X and A. So since I have 3 out of 4 of those things, I should be able to find the fourth one. So I'm sure that some of you can look at the list, find the right equation, and move on. My experience has been that this is a place where students sometimes get stuck. They don't know what equation to choose, so I'm trying to give you a strategy for choosing the correct equation. And that is check off all of the pieces of information that you have in the equations. So check off delta x, VI, and VF. So I have delta x, I have VI and VF, VI and VF, VI and VF, and delta x, and VI. So I cannot use the first equation. I'm missing V average and T. I could use the second equation to get V average, and then once I got the V average, I could use it up here to get T, and then once I got T, I could use it over here to get A. And that would be a 3-step process. Use the second equation to find V average. Once you have that, use the first equation to find T. Once you have that, use the third equation to find A. That is a perfectly legitimate way to solve this problem. And some people might choose to do it that way because it avoids having to deal with the fourth equation, which involves squares. And, perhaps that's seen as a little bit more difficult. So maybe a 3-step process with easier equations is better than a 1-step process with a harder equation. We're going to go ahead and do the problem with equation 4. We have VI and VF and delta X, and we're going to use this equation to solve for A. It's not possible to use the last equation because you don't have A or T. All right, so it's possible to use the second equation, and it's possible to use the fourth equation. If you use the fourth equation, you can do the problem in 1 step. If you use the second equation, you can do the problem in 3 steps. You'll get the same answer either way. I think this problem is a good example of the fact that it's often helpful to draw a picture of the scenario that's being described. So if you draw a picture of the rifle with the bullet in the rifle and think about where it is at the beginning of the problem and where it is at the end of the problem, you know this distance. You can figure out that the final velocity is the velocity as the bullet leaves the gun. That's how we know that the 600 is the final velocity and not the average velocity. It's often helpful to draw a little picture to accompany your problem to kind of piece together, the meaning that all of those values have. Okay, we know VF squared, that's 600 meters per second quantity squared. And we have VI squared, which is 0. 0 squared is 0, plus 2 times A times delta X, which is the length of the barrel of the gun, which is 0.75 meters. All right, so this is what we're going to solve. So let's simplify a bit. I will first square 600. That's equal to 360,000. 360,000. The meters and the seconds get squared as well. And that number only has 3 significant figures. So in theory, I should be writing it down like this: 3.60 times 10 to the 5th. But I'm going to leave it like that and just remember that it has 3 sig figs, because I don't do the rounding until the end anyway. The meters got squared and the seconds got squared also. 0 meters per second squared is 0, and when I add that 0 to this piece, it's not going to change that piece. So I'm going to leave that out in my simplification. I can multiply the 2 times the 0.75 using the associative properties. You remember that A times B times C is the same as A times C times B, right? You can, well, maybe we'll write them in the same order, A, B, C. So we can multiply those guys first or those guys first. It doesn't matter when we multiply things what order we multiply them in. So it doesn't matter if we multiply A by 2 first. We can multiply 2 by 0.75 first. So 1.5 meters times A. Sorry about that, little problem there. 1.5 meters times A. Okay, so now we're going to divide both sides by 1.5 meters. So A is equal to 360,000 meters squared over seconds squared divided by 1.5 meters. So I still have that number in my calculator from before. Divided by 1.5 is equal to 240,000, which is the number we were expecting because I gave you the answers. So 240,000. That number is supposed to have 2 significant figures now because of the value 0.75 meters. When we doubled that, we got 1.5, but that had 2 significant figures. So this answer can only have 2 significant figures. So I don't have to write it in scientific notation because none of those zeros is significant. When I divide meters squared by meters, it won't be meters squared anymore, it'll just be meters. And so my answer will be in meters per second squared, which is what's expected for an acceleration. It's a huge acceleration because there's a giant change in the velocity from 0 to 600 meters per second in just a tiny amount of time. We chose this equation because we could do the problem in one step, but I think there might have been some value in doing it the longer way, where we got the average and put that in here, and got t and put that in here, because we would have been able to see the value of the time is very, very tiny. So the bullet has a huge change in velocity over a tiny amount of time. So that's going to result in a huge acceleration. 240,000 meters per second squared.